Thank you. Thank you for the introduction. Thank you for the invitation to this nice conference. So, as I told Birgit and Roland earlier, it's my first time in Vienna, so I'm very lucky to see this gorgeous city with such a beautiful weather. Okay, so I'll speak about again about Korteweg-de Vries equation, the modified one, so the cubic one, and I will be interested in self-similar solution and the flow around self-similar solutions. So this is a joint project with Simão Correia, who is in Lisbon, and Luis Vega, who is in Bilbao. Okay, so this is the parts on the talk. So I'll mention very briefly some physical motivations from fluid dynamics. I will give some description of self-similar solution, and specifically in Fourier space, Fourier variables. And I'll try to convince you that if you're interested in even in local well-posedness problems, then self-similar solutions are a pain, actually. And then I'll speak about perturbation of blowup. That will be the heart of the talk. Okay, so the physical model that I'm interested in is these curls of smokes. And okay, so you can think that what is relevant here is the filaments, right? The vortices filaments. And okay, so the basic question is, can you understand why these kinds of filaments form and how do they evolve? And of course, you have the equation from fluid mechanics, which is a big system. So you'd expect that you can describe vortices filaments from there. And the idea is, okay, can you get simpler models, simple asymptotic models maybe, or using dispersive PDEs to understand this, like a simpler thing. So one proposition was to use the binomial flow, and this is very natural. So it's this equation. So it was introduced maybe a century ago, and then I guess it's Luis Vega who put this model up, and he worked a lot with Valeria Banica on this. And the point is that if so, this is the it describes the curves. Then if you take the curvature of the curve, then you get somewhat cubic 1D NLS with a perturbation, but it's essentially cubic NLS. Another model. In fact, you have a hierarchy of model, and maybe the binomial flow is the first step. The second order is this thing, and again, if you look at the curvature, then what you get is the mKdV, and maybe the mKdV is a better model, not only because it's second order, but also one thing you have formally on the binomial flow is that the length is preserved, the length of the filament is conserved, and if you expect to have filaments, then maybe the fact that the length is conserved is not so good. Okay. In both cases, anyway, the spirals corresponds to self-similar solution for the curvature. So they appear, self-similar solution appear for these problems rather naturally. Okay, so this motivates self-similar solutions for mKdV. So mKdV is very similar to the KdV equation, except you have a cubic nonlinearity here. Epsilon here is just plus or minus 1, which corresponds to focusing or defocusing case, but in here there won't be very much difference between the focusing and defocusing case. It doesn't really matter for the analysis that I will do here. Okay, so let me go very fast on this, as Herbert just gave a lot of insight already. Okay, so let me underline again that for smooth and decaying data, then you can use really integrability, and you can prove many beautiful results. The trouble is that self-similar solution there will be essentially rough data. So it's really hard to use the inverse scattering for this. Okay, so let's speak a bit about self-similarity. So there is a scaling invariance for the equation, which is this one, which is nice. It's an L1 critical equation, and I believe L1 critical equation, well, self-similar solutions are very relevant for L1 critical equations. Of course, you have a self-similar solution for as soon as you have a scaling, but when you are L1, then probably it's physically relevant, and it's probably the reason why you get cubic NLS, 1D cubic NLS, and also a cubic mKdV. And the equation now is h minus a half critical, so KdV was h minus 3/2 critical. Here it's h minus a half critical. The numerology also plays a big role here. Okay, and the self-similar solution is just something which is invariant by scaling. So it's something of this form. And you can see that you have a blow-up at 0 here. If you put this ansatz in the equation, you see that you have derivative everywhere, so you can integrate once. And if you integrate once, you get this, which is the Plain-Levé 2 equation, and you have a constant of integration, and the constant of integration will actually play a role, so it is important in this business. So I don't know if, okay, I can tell you already, the constant of integration plays a role, so if you remember the pictures, so this is a big corner, right? If alpha is 0, actually you don't have a corner. So you have the filaments, but it's on the line. If alpha is not 0, then you do have a corner. And actually corners are important, so you're interested in what happens for alpha non-zero. Well, in the following of the talk, alpha will be small actually, so it will be a small perturbation of the straight line. It won't be corners like harsh corners like this, but still a little corner. Okay, so the constant is important. So as I mentioned, it's an L1 critical equation. So this is what I mean by saying that self-similar are somewhat critical. They have a blow-up. They have blow-up at 0. It's at the linear level even. I repeat that they describe vortices making a corner for fluid dynamics. Maybe. And they also appear naturally, even if you're looking at very smooth and very decaying data, they do appear in the description for a long time, for the long-time dynamics. So the long-time dynamics of mKdV, even for small solution, especially for small solutions, it's not linear. You don't have linear scattering because it's critical. You have the critical decay, 1/t decay. So what you get is a modified scattering. And this modified scattering gives you logarithmic oscillations. And when you have this oscillation, then you can describe the long-time behavior into the regions, into several regions. You have the soliton regions, you have the dispersion region, and in between you have the self-similar region. And in the self-similar region, your small solution will show a small self-similar data. So however smooth you start, in the end, you see something of an object which is, I will explain why it's not so smooth. I mentioned already, in other context, I mentioned the work by Banica and Vega for the Schrödinger type equation, for the binomial flow. And let me also mention for wave type equations, there were a lot of study of self-similar blow-up. Maybe I can mention the work by Mel and Zag on the study of the blow-up curve and for the nonlinear wave equation, and at each blow-up point, the blow-up profile. And there's also a sequence of work by Donninger and Kuba and collaborators for stable self-similar blow-up in various cases of wave type equations, wave maps, and stuff. Okay, so maybe in both cases, however, there is a nice transformation that makes the problem easier. For NLS, you have the pseudo-conformal transform. which will turn your self-similar solution to a constant solution. And if you have a constant solution, then, well, it's okay, you don't have decay, and you expect that you don't have decay at infinity, but if you differentiate, then it's 0, so it's nice to differentiate. And yeah, this makes it easy. For wave type equation, and this goes at least back to, I don't know, it's very, very, very long, but if you look at self-similar solution, you're naturally prone to study what happens inside the light cone, and inside the light cone you have Lyapunov functional. And for example, you have energy decay inside the light cone, you have radiation outside the light cone. Another way to say this is that you have Lyapunov functional, and then you enjoy some parabolic properties inside the light cone. So it makes the work in self-similar variables possible. I mean, you have very, very nice descriptions in both these works, and really this is possible because you have Lyapunov functional. For mKdV, you don't have such tricks. So you don't have a transformation that turns self-similar solution into something really nice. You don't have Lyapunov functional, so you have to dive into computations, which can be also hard in the earlier cases, but mKdV is, at least for me, it was really painful. Okay. Okay, so the first thing is you want to say, okay, self-similar solution, they will enjoy some property which are very similar to that of the linear equation. And the self-similar for the linear equation is simply the Airy function, which will generate the linear group. So the Airy function is this oscillatory integral. And, well, there is a very nice description. So you recover the constant C and the alpha. Yeah, this is what so you have this picture of the Airy function. So, well, it's essentially a phase, stationary phase argument. So you have a lot of decay on the right, and you have slow decay with a lot of oscillation on the left. So in the space variable, it's not so nice. So the Airy function is not in L2. So it's in LP, but only for p greater than 4. If you need to differentiate, then it's even worse, because any derivative will cost you half, an x to the 1/2 increase. So actually, what is nice, for example, is that the product of Airy prime times Airy is a bounded function, because the oscillation exactly kills one another, and the decay exactly kills one another. So. But yeah, the derivative, if you differentiate, this is in sharp contrast with the binomial flow, for example. When you differentiate, you get something worse. So the idea, so yeah, here are more specific asymptotics. So this was Airy, and for a self-similar solution, you have basically the same asymptotics, at least for data which is not too large. So this is the result by Deft and Zhu, and using essentially the Riemann problem and integrability property, and they say, okay, if I give myself an asymptotic behavior at plus infinity, spatial plus infinity, then I can describe the behavior at minus infinity of the self-similar solution. And if this parameter kappa is too large, it's greater than 1, then actually you don't get a global solution, you get a meromorphic solution with poles. So this is the case when alpha is 0 and in defocusing. If you want to have alpha not 0, then all this Riemann problem work just collapses. And there is a nice paper by Perelman and Vega who describe the asymptotics in physical space for a small first parameter and small alpha. Yeah, small average of S. So these are only ODE techniques. Okay, so this gives the description in physical space. So in physical space, the picture is not very nice if we want to study the flow. So we said, okay, so what about, we want to do some stuff in Fourier space. So what about Fourier space? And this is the first result that we obtained. And okay, so you look at a self-similar solution, which is small in the sense of these two parameters. So C is the mean value, and alpha is the constant of integration, the corner. You take out the oscillation that are given by the linear flow, and this is essentially the Fourier transform of the Airy function. So you have a perturbation of the Airy function, and this is this curly S, calligraphic S, is what we will call the profile. And you see that you have the logarithmic oscillation. So over the Airy function, you have logarithmic oscillation, and this is reminiscent of the modified scattering. It's really linked to the modified scattering. So, well, we'd be happy with the first order. However, to do the proof, doing an expansion in L infinity without the derivative is not enough. You need to do, well, it's all stationary. It's heavily based on stationary phase arguments. So you need some integration by parts. So you need to understand the derivative. And if you do the derivative, then you cannot differentiate only the first order. You see that you will need the second order. So the second order, if you differentiate it, so the worst that can happen is when the differentiate goes on this oscillatory term, and then you get you get xi squared over xi cubed, so 1 over xi. And so these terms for the derivative contributes. Okay, and this is why I formulate the result like this. And another way to see that you need a lot of faith and a bit of luck is that we were able to perform the analysis with this. There is a remainder, and for things to work, you need the remainder to have this decay, and this decay you have to tune it. It's fine-tuned between 1/2 and 4/7, so you don't have a lot of room, right? Okay, so this is what happens for large psi, and for small psi, then you don't have any oscillation any longer. So this is a difference also with the binomial flow. And you see that the alpha the non-zero alpha correspond to a jump in frequency. So you have a jump at 0. So it's not continuous, for example. But it's okay, it's not continuous, but it's not oscillatory, so it's a nice discontinuity. Okay, and of course, as we're looking for only the real mKdV, the complex mKdV would be a different story. So knowing what happens for xi large is positive, means that you know also what happens for negative xi. Okay, so maybe I did one slide, for the following on some insight of the proof. So you want to solve this. So you want to look at the Fourier side. So it writes like this. The constant alpha turns into a Dirac, and you write this convolution in terms of the curly S, which is the profile, which is, again, this guy. And what you want is a fixed point here, where n is your nonlinearity, and you see the face appearing. It will appear a lot here, so it's a cubic face. So you have a lot of resonance, and you have to study a lot of resonance. And okay, so the trouble, as I told you, was to find a good ansatz. And in this setting, constants are just the Airy function. So you start with constant, you plug it in this guy, and you see appearing the logarithmic oscillation. So it gives you the first ansatz. You put logarithmic oscillations, and what you get is logarithmic oscillations. So here you're very happy. However, if you want to control the error term, and which you will need to do because it's a fixed point argument, you need integration by parts, and so you need to control the derivative. And then comes the trouble. So because if you put the derivative on the logarithmic oscillation, then you don't get what you expect. You don't get it because you need the second term. So you need to reduce things, and in fact, it means going to the second Picard iterate, get the second order expansion, differentiate, and then this you recover what you've put in. So it bootstraps, and you can do a fixed point argument. So the estimates on the error is really crucial here. And okay, this was the only thing on there that I wanted to tell today on the self-similar solution in Fourier space. Okay, so now I will try and convince you that we constructed self-similar solution, and then you want to know about the flow around self-similar solution. And I'm now trying to convince you that it's hard. So let me review a bit the local West-Posnes theory available. So there is this seminal work by Koenig, Ponce, and Vega, which gives you local West-Posnes in HS for s greater or equal to the fourth. And of course, scaling is -1/2, so you're far away. But if you want to do fixed point, then you cannot go below this 1/4. There is this deep result by Hub, Griffith, Killick, and Visan, which almost managed to go to the scaling. But they slightly miss it, right? And also, it's not really a strong local West-Posnes result that you get. So to study the flow, it's not so easy, right? It's really the same kind of solution that Albert told us about in the previous talk. So, and this is already very deep. On the other side, if you think that maybe the HS scale is not what you need, there is this nice result by Grunrock and Vega on Fourier-Lebesgue spaces. That is, the Fourier transform is in some R prime, and you add some weight. And here, so it's still intricate, but they also almost manage to get to the critical space, but they miss it. The critical space would be R is 1 and S is 0. So if you put R is 1, the S is okay, but you miss the R is 1. And R is 1 is just, H hat, H01 hat is just U hat in L infinity. And this is really the nice space, because the self-similar solution belong to L infinity. So you remember they have these oscillations, a lot of oscillations, and the jump, so not continuous, but they're bounded. Okay, so we slightly missed this. Okay, then the other thing is, okay, maybe I don't have local West-Posnes in big spaces that contain self-similar solution, but maybe what I could do is look at nice perturbation, smooth perturbation around a self-similar solution. That is high regularity around a rough background, right? And the point is that it fails also. So at least if you try and do naively. So let's try and do it on the toy model. So you look at the linearized equation around the linearized self-similar solution. So this means around the Airy function. So you look at the linearized equation, which is written in Duhamel form here. So U is the rescaled Airy. And say so you're in the context of you can assume that you will do really nice perturbation. So let's use the best available dispersive estimate that you get. Which are the Koenig, Ponce, Vega estimates. Okay, so you look at the L2 norm, and the L2 norm tells you that you can place the nonlinear term, so you gain the derivative, which is the gain from the dispersion, and you can place it in these KPV space, L1 in X, L2 in T. So time and space are inverted. Then for this nonlinear term, you cannot do much better than using Hurler inequality, and you would like to put the rescaled Airy function in this guy. But if you look at one fixed time, then the Airy function is not in L4. So again, you barely miss L4. It's critical. Everything is critical in this business. So for each time you miss L4, so if you take the sup in T first, of course you miss it. So this barely fails, but it fails. Okay. Nevertheless, we were able to to do a local well-posedness results in a space which is critical and contains self-similar solution. So it's not the super nice local well-posedness result that you expect, but still we get a solution. And we have forward uniqueness. And continuity of the flow is maybe slightly unclear. The point is to work in these spaces, so the Fourier transform will be bounded. So this should be at infinity. So yeah, it's not the right space. All right. Here the Fourier transform you allowed a jump at 0. So it's not continuous bounded. It's continuous bounded except at 0, and at 0 you have limits on each side. And then you need to have some regularity on the Fourier transform that is like xu is in L2. And the norm that you have to put on this is this norm, is this critical norm, where you have the Fourier transform is in L infinity, and the H1 dot norm, so you can forget of it. I put the oscillation because what you really want to see is the profile, so you have to kill the linear evolution. But of course, when you take norms, it doesn't play a role. And here, of course, this is not scaling invariant, but if you put the right power of t, then it is scaling invariant in the sense that if you look at the u lambda, so lambda what they rescaled of u, in this space E, it doesn't change with lambda. Of course, it changes the point where you look at, but it doesn't change. And the idea was to revisit the modified scattering theory by Hayashi and Naumkin, because these kind of norm already appeared, but they have also H1 and much more regularity. So we had to retake all the arguments and to clean all the estimates. And then if you kill the uncritical norms, then you don't have a true solution to start with. So you have to work on an approximate problem, and because you always need to have a priori estimates. And the approximate problem, then you have to be a bit careful. It's like you truncate in Fourier space, but you have to truncate. The truncation cannot be anything. It cannot be compactly supported in Fourier space, so you have to be a bit careful. Okay. Yeah. Time of blowup is 0. So you give yourself your initial data at time 1, and you look at around 1, and you would like to go up to 0 if you want to study. Yeah. So yeah, if you look at at large times, then for example for small data you do have the same modified scattering for large time. But if you want to look at blowup, you would go reverse in time to 0. Maybe we should try self-similar coordinates. Yeah. Well, when you write the face, maybe I will try. There will be some answer in the next problem, because we'll use really here. It's a mix between stationary phase argument and L2 energy estimates. In the next thing, it will be much more really writing the oscillatory integrals, and then you see the self-similar structure much more. So maybe. Okay, so this was well-posedness and self-similar solution. So now let's turn to the question of the talk. So for blowup stability, there are two questions that you can look at. Either you give yourself initial data at time 1, which is a perturbation of the self-similar data, and you have this perturbation D1, and you want to go to 0. And say that around 0, maybe not at 0, maybe the time of blowup can change a bit, but you'd say you have blowup near 0, and you want to study the blowup behavior. This is one question that you can ask. And the second question is probably simpler because it's the one that we did, is, okay, you want to construct a blow-up solution, so with blow-up at 0, but with somehow of a prescribed behavior. So what is the prescribed behavior that you can have? You have the self-similar blow-up, and then you want to prescribe somehow the regular function that you get when you extract the blow-up. So the question is, you give yourself the regular function, and can you construct a solution u of t such that if you subtract the blow-up, then you converge to this regular function? Okay, and I will mostly address only address question 2 here. And of course, the functional space, as I mentioned, is really important. And actually, we have 2 theorems. So, and the idea is to compare the functional space involved. So the first theorem is loosely based on the previous one. And it goes this way. So if you take your perturbation, which is really nice and decaying, small, you give yourself a small self-similar solution, then you can indeed construct a unique perturbation. So the solution will look like, will be of this thing. So u of t is the self-similar solution plus the fixed thing plus w. So the remainder w is meant to go to 0 as time goes to 0, and you have we have rates, right, in the critical norms, and also in L2 because here you have a lot of space to be in L2, and it's really, you can see that it's a perturbation because you see here you have a cube. Okay, so and then it means that you have convergence in these spaces. So in particular, the E of t gives you convergence in the infinity norm for the Fourier transform, and the L2 is the L2. Okay, so we were already happy with this, but still we had a second result, and the point is, okay, can we remove? One of the basic questions was, okay, this guy is like really subcritical, so it does not have a lot of sense that it's really small, and okay, can we remove the smallness assumption on Z? For S, it's a different business because S is really, it sits here. So there is no decay at all. It's critical. So if you take large S, it's really unclear what can happen. Also, the description that I gave you of self-similar solution is only valid for really a small self-similar solution and not for any self-similar solution. Okay, so this is the second theorem that I will tell you about. So the description here changes a bit because everything will be done in Fourier space. So now this will be the description. So I put a hat on the U, but I don't want to put Fourier transform everywhere on the Z and W. And here, okay, I will really look at the profile. So in fact, it will be the curly S. It's the, I don't know if you, okay, let's say it will be the curly S, but everything is done in Fourier. Okay, and the idea will be to work only in Fourier space, and the functional space will be based on L infinity, weighted L infinity spaces. So it goes essentially as before. So you give yourself a perturbation. I will talk about the spaces afterwards, and you construct a unique solution in the space, which tends to 0 when t tends to 0, and you have the delta cube, and you have this rate gamma, such that you, like this, is a distributional solution of mKdV in the right sense. And what you gain from the previous theorem also is a stability estimates. So if you give yourself 2 perturbation, then the unique solution that you constructed actually satisfies these stability estimates. So you can see the cube. So now you have only delta squared because you have this other one, delta. Okay, so now about the spaces. So L infinity mu is just the weighted one. The W1 infinity is the mu and mu prime. Say that the first index here say that the function is in infinity with a weight mu, and the second index is for the derivative. And most of the time, it will be the same index mu. It will be W infinity 1 mu mu, and when it's the same index, I only put 1. The only times when there have different index is for the self-similar solution. So the self-similar solution, you have 0 decay for the function, and you have 1 over psi decay for the derivative. So it's W1 infinity 0, 1. So this is why you have this norm that appears here, and as you have to allow the jump, then the norm is taken outside of 0. This is a distribution. If I look at the restriction of this distribution outside 0, I want it to be in this space. Okay, and it has to be small. So the fact that this norm is not very important, it just means that the self-similar solution are given by 2 parameters, C and A, and it just means that the C and A must be small, and I say that the smallness is given by delta. The Z has to belong to this W1 infinity space with weight nu. So I have several parameters. So you have to think of nu very small, near 0. So what you're interested in is really near critical things. Critical things are when you have no decay. So you have to think about nu positive, but very small. And then you have a bit of loss because it's large. So you have to expect that you have a loss. So you give yourself a mu, which is also positive, but strictly less than nu. And the solution, the perturbation that you will construct will lie in W1 infinity mu. And all the bounds will be obtained in this mu weight. Okay. Okay, and then there is an extra parameter. So you give yourself the nu small, then you get the mu, and from the mu, you get the gamma, and the gamma is related to the rate. And so the gamma is even smaller. So you want to make gamma as big as possible. So, okay, so I will make some comments. Yeah, so the thing is we're happy about this is, okay, it's almost critical spaces. We only need to have a new decay, and the Z can be chosen large. Yeah, I should mention that this kind of problem, constructing a solution with a prescribed blowup, there was a result by Gutierrez and Vega for the binomial flow. But in their work, so they have you have to rewrite in the right knowns, but it's essentially the same ideology. But here they have to choose not only a small self-similar solution, but the perturbation has to be small, and small with respect to the small self-similar solution. So you have 2 scales. So yeah, in the first result, we had only 1 scale, and here there is only the smallness on S. So one natural question is, okay, with the method that we developed, could we do a large regular solution for the binomial flow, for the NLS? Okay, so I mentioned that it's probably very hard to get around the smallness on the self-similar solution. The thing is to construct a solution and around the rough background of S. So it's really how it has to be understood. And also, as you go through blowup, as you tend to zero near 0, then you can go also in negative time with the same Z, but negative time. So you actually could construct a solution on minus TT. So it's always nice to go through blowup when you can. Okay, the main ingredient here is, so we'll do everything in Fourier space, and so we have to forget about L2 based energy things. And we derive a new procedure, and the idea is to use the infinite normal form reduction, ENFR. which the idea is to capture time oscillations. If you use the previous thing, we use only decay in time, but here it's like, so we will do perform integration by parts in time. So the NFR was notably developed by Kwong and Ho, Hiro and their collaborators, and also Kishimoto. And there was an early work by Dabi, Nilin, and Titi, also with the idea of using integration by parts in time. However, in these works, so the NFR uses a solution that you already have. So they only give you a priori bonds. And the way it has been used for is to derive, for example, unconditional uniqueness. So you give yourself two solutions. Often when you have local warplessness, you have like you give yourself an initial data, but the solution that you construct enjoys better regularity that you get through the dispersion, the spaces that capture dispersion. If you give yourself a solution that is only continuous in HS and no more, do you still have uniqueness? And the NFR answered this question, usually positively. And here we really construct solutions. So we'll use it to have a priori bond on an approximate problem. But I believe it's the first time it's used, well, at least one of the first time that the NFR is used to construct solutions. And yeah, in the end, we construct solutions, but first we have to work on an approximate problem, and in the end, it's a compactness argument. Okay, so let me give you some insight on how the ENFR develops and works. So yeah, first, so it's a big bootstrap argument, and I have to explain. Okay, the bootstrap. So okay, so this is my nonlinearity. So you have the phase that was introduced earlier also for the self-similar solutions. But now the function also depends on time here. And h psi is my hyperplane of convolution. And what I want to solve is w of t is the integral from 0 to t to this thing, because the z does not depend on time, and the s is a self-similar solution, so it solves the equations. And I don't have, well, w of 0 is 0, right? The point is that, yeah, what I want is it goes to 0 at 0. Okay, so what is the bootstrap? The bootstrap is that you have to assume some rate with a small constant delta on some small interval of time. So t is a parameter of the bootstrap here also. And you want to improve this by recovering the same decay in time, but this time not with delta, but a cube, delta cube. So you gain. The gain is in here. Okay, so what will be the estimate that you get on the other function? The s, well, it lies in this space, so I should put also r without 0. So it's small, but there is no decay. And the z can be large, and the only way that I will use that z lies in a subcritical space, I will only use these estimates, and these estimates will essentially give me the t. So of course, this guy goes to infinity, so I can put a delta here and look at a small interval of time. So in fact, what it tells you is that, okay, I look at the z, which does not depend on time because it's meaningful for the problem, but I could look maybe at a z of t, which has a subcritical, which tends to infinity in a subcritical space and in a subcritical rate. Okay, so this is the only thing I use. Okay, so I will focus on this equation. So let's write it. And the idea is to do integration by parts in time when I can. So let's expand this term. This is a trilinear function. So I expand the term, and maybe I look at the term with s, z, and w. One s, one z, and one w. So z does not depend on t. So you split in frequency. So you put a frequency. So the phase is less than n1 or bigger than n1. And here you have a resonant term. So you'll try to bound it directly. And here, it's a priori a large region, but you have a gain if you integrate in time. I'm sorry, I forgot the face here. Of course, there is the faces. If you integrate in time, you gain 1 over phi, and as phi is big, then you gain 1 over n1, essentially. Okay, so yeah, there are the phases. So let's focus on the resonant term. And for what is crucial in this argument is what we call the frequency restricted estimates, which is this estimates. And if you look closely, you see that there is no function here. So basically, it's just a computation of an integral. And this is because we work in N-infinity base space, one pointwise estimate in space. So when we have to estimate this guy, what we do is we put L-infinity bounds here, weighted L-infinity bounds. So for the integral of I of s, and there is still the face. I'm sorry, I pissed off the face. So S, you have no decay. Z, you have, okay, you could put mu decay or nu decay, L infinity nu, say, and W L infinity mu, and you put the decay here. And what you want to recover is mu decay, so this mu is related to this, and you have one derivative, the psi here. So this frequency restricted estimate is really the key, right? So it allows you to estimate the I without the integration in time. So you do the computation. Here you have nothing, you have a delta. Here you have the loss, you have a delta and the loss minus rho. And here you have the gain gamma. Right? And for the integral, you have the gain 1 minus mu over 3, so n1, 1 minus mu over 3. Okay, and the idea is, okay, what do you want to do? Okay, I forgot to mention, we will do in the end integration by time, by parts in time, and we don't want to bother too much. So the frequency has to be dependent on time, of course, but it's easier to work on dyadic interval in time. So I will only work on tk plus 1 tk, where tk is this guy. I integrate between tk and t lies in this interval. So n1 will depend on, so time, t and tk are of the same order, and I will choose n1 to be essentially 1 over tk plus 1, so I gain 1 over s to the power 1 minus mu over 3. And this mu over 3 gains over the rho, and what I get is s to the gamma minus 1 and delta cube. And then I have to integrate in time, and when I integrate in time, I get t to the gamma. So this bootstraps. I have my gain of delta squared, delta cube. I started with delta and I get delta cube. So this is good. And this is what will happen essentially all the time. So now let's look at the non-resonant term. So I do the integration by parts in time. So here I put the face. Good. So I have this gain and I have the bracket. And then I need another frequency restricted estimate, but it's really the same. It's really a corollary because I have this gain on the face. So just to prove this guy, I say, okay, it's the sum. I decompose dyadically in M, and this M, I got a gain on the denominator, and then I use a resummation argument, and I get this. So the real one is this one, is this frequency estimate, which is a lot of stationary phase because there is a phase that I forgot to write down. And you have to be, well, I had to be very patient to get this, but then this is really a corollary. Okay, and let's look at this term, if we can bound it. So you have the derivative in time on the nonlinear term. So say that the derivative goes on S. So this should be a curly S here. So if it goes on S, then I have to use the bound on the derivative on S, and I pay a price, which is 1 over S, but I get the delta. However, I gain the 1 over phi, I gain this thing. And so in the end, I get exactly the decay that I want because I need to integrate the same, I need to integrate in time, so this kills the minus 1, and I get t to the gamma times delta cube. So this works smoothly. For the bracket, it's the same because you don't have the bad decay in S, but you don't have also integration in time, so it's the same. When the derivative in times goes on z, it's the same. You have nothing because z does not depend on time. And then what happens when the derivative goes on the w? Well, here you use the equation for w, right? And you change the w by its nonlinear expression. Right? So what I did here is, okay, I started with the w, and you see a tree shape appearing on this term. So I had the w at the beginning. Then the derivative can go on this, which I treated. So this one is fine. Then the derivative goes on d, it's fine. And then when it's w, then I have another tree, right? So let's look at another term here. And it's the term when you have SSW. So I choose this one because this one is a bit different. When you have S and S, you should not treat it as a trilinear term, but you should put the two self-similar solutions together to get extra cancellation, and it will give yourself this kernel K0. So K0 is related to when you integrate first the two self-similar solutions. So it's a bilinear term, and it's the same business. So you have another face, which is this one, and you integrate on the line. And okay, and so what you get is a new face, which is the sum of the earlier phase and the new phase. And you have to restart. And let me just explain to you how the estimate propagate. So I will look at the resonant term. So the resonant term is, so you have this S and Z, which corresponds to this guy. And then I have the K0, which is the SS, and the W. You have this new phase, the theta, which is the sum. You had integrated in space once on the first phase, in a time 1, which gives 1/phi. And you had, it was the non-resonant term for phi, and then it's a resonant term for psi. Okay? And you integrate over a new space, which is the product of the two convolution things. So it's, yeah, it's okay. And you have this convolution hyperplane. You use your restricted frequency estimates. Well, you put L-infinity bounds first. So you put everything you can in L-infinity. So you have to be careful because you have so you have to derive the asymptotics for K0. So K0. And K0 has its own asymptotics, which is essentially phi to the -1/2. But you don't have a Japanese bracket. It's really psi. It's really, you recover the self-similar structure. So you have to put this guy like this. And okay, this is the weight that you get. And what you see is that you will have a cancellation here, the psi3 over the psi3 here. And these cancellations, this is what will allow you to propagate the estimates. So when you want to estimate this integral, you have to look at what are the variables involved. And actually, you can see that you can put this the variable of integration which appear to the tree on the second layer first. You do your so here it's a restricted frequency estimate on psi with something which is fixed. Here it does not depend on the psi3(1). It depends on the early variables. So this is the alpha. This is the role of the alpha here. So you put your estimates, and you get something which decays in n2. You get n2 to the 1/2. And here, you get the n1 to the -μ/3. And this is exactly what you need to be in business, because this guy kills exactly the guy that you get here. Okay, so this propagates from level 1 to level 2, and actually you can perform the same thing by looking really what are the variables of the integration. And it works fine for almost all terms, except one term, which is the source term, which is one source term, where when you integrate in phase, you don't gain nothing. And remember that on Z I have a loss, so I have to recover something. And for this, well, you need to integrate in you need to integrate in the Fourier variable in space, but the space is Fourier. So you need to do an integration by part in space, and this is possible because this region is nice, and it's not, the phase is non-stationary here. So you have a tree with a lot of terms, and you have to treat carefully each term. And in the end, if you fix yourself an order, then you have all these terms that are given by the NFR, which is the resonant one, which is nice, the boundary term, which is nice, the derivative term that are nice, the F2 terms that are actually the well-behaved terms because the tree stops on an F2, but they require some extra regularity on Z. And then you have the remainder terms. So this one is fine also, and you have the remainder term. Okay, so you can estimate, so I'm almost done. Okay, almost. Then it's essentially technical, but let me just say one thing. The important thing is to prove that the remainder tends to 0. So I cheated a lot in the proof because this is an a priori, what I showed are a priori estimates. And I want to construct a solution. So I need to look at an approximate problem, and the right way is to put some cutoff function, a bit like for the critical local well posedness. And for this equation, this one is really well posed, there is no trouble, and it gives you a mild control near 0. So when Wn of 0 is 0. So you have a mild control, which depends on n. Awfully depends with a huge constant in n, but it tends to 0 in 0. So if you fixed, so you have to put n's everywhere. If you fixed n the time k, then you can prove the mild control that you have allows you to prove that in some norm, the remainder tends to 0. And then the expansion goes to infinity, and this is why you have the infinite normal form. This is true for all n and all k. So you pass to the limit in n, and you get what you want. Okay. And then, well, you have a bit of work, but the sequence on WNs, they have the resonant extra ingredient. I want to pass to the limit in n using one Ascoli argument. And here I did everything in L infinity mu, and it's not quite enough. I need some bounds on the derivative. And the way to do this is to use the scaling operator, which is the dilation operator, which was heavily used also for the L2-based energy estimates. And the point is that you can do the NFR also on the equation satisfied by lambda u, because this goes through the equation very well. So it works for lambda w, and you get all the estimates you want, and you can conclude by Ascoli. Okay, sorry for the delay, and thank you for your attention.